Hello, good evening. I'm Cindy Ebinger. I'm president of the Tectonophysics section of AGU. I'm very proud to present today's speaker for the Birch lecture. And we will also, well, we've had to make a few changes, some very last-minute changes, because many of you may have spotted that this lecture is listed both at 4 o'clock and at 5 o'clock. And even internally, it wasn't clear when it was going to be until just a few moments ago. But we are going to have it now. And what we'll do, Kai Johnson has been an amazing, has been through a lot today, I'd just say. He's actually giving a presentation in another section at this very moment and doesn't know that he isn't on at 5 o'clock. So we can all surprise him when he comes down. No, that's probably not a good thing. But I'm going to just announce for the first time, the Tectonophysics section has an opportunity to recognize the great talent in the younger or earlier career scientists. And so Kai is our first ever Tectonophysics section early career scientist. The citation is there, and we'll bring this back up at the end, I hope. But in case this slide doesn't come back up again, I just say that his citation is Michael Hamburger. Just summarized all of this in that statement. He has a breadth of scientific interest, the depth of his understanding of geodynamic research problems, his technical creativity in finding innovative ways to address them, and his generosity in sharing ideas and successes with students, postdocs, and collaborators. And I think that this slide of the happy group of graduate students just demonstrates the generosity that Kai shares with all of his graduate students. So, and his colleagues as well. So in absentia, we can congratulate him, and then when he comes, we can also congratulate him as well. So okay. And then what I'd like to now do is introduce, whoops, not quite sure.
Would you bring the other slides up for you?
Yeah, well, the next, it's on the Mac, right? But, okay, sorry. And now it's my great pleasure as well to introduce Jerry Mitrovica, who will be giving the Birch lecture today. Now, I have to acknowledge that I searched for background information on Francis Birch and have used some information that I found on Wikipedia because I thought it was actually very appropriate. He's a Harvard professor and a former GSA president and worked in high-pressure mineral physics and provided quite a great deal of information on the structure and composition of Earth's mantle. And I thought it was also quite appropriate to comment that he had a great sense of humor as well. And a footnote to one of the most highly cited papers says, unwary readers should take warning that ordinary language undergoes modification to a high-pressure form when applied to the interior of the Earth. A few examples of equivalence are below. The high-pressure form of dubious becomes certain, and trivial objection becomes unanswerable argument. So I think that today's speaker, Jerry Mitrovica, in many ways has some parallels. Jerry has a brilliant sense of humor, as many of his colleagues and collaborators know also well. Jerry also has a certain dramatic sense that comes from an early training. He also works or is deeply interested in Earth's mantle. And I'll just give a brief summary of his very auspicious career to date. Jerry holds a bachelor's degree and a master's degree from the University of Toronto. He was a Harvard-Smithsonian Center for Astrophysics as a visiting researcher. He's also been a visiting scholar at the University of Milan, and he was elected a fellow of the American Geophysical Union in 2005 and a fellow of the John Simon Guggenheim Memorial Foundation in 2007. He received the Rutherford Memorial Medal in Physics from the Royal Society of Canada. In 2008, he received the European Geosciences Union Augustus Love Medal. He served on many editorial boards, including Journal of Geophysical Research and G-Cubed. He was just recently at the University of Toronto and has now moved to Harvard. And I just share a very brief anecdote, and I'm sure that all the Canadians in the room will, and some of those of us from the northern parts of the U.S. as well will appreciate this, but I understand his young niece was really excited to hear that he was going to work at Harvey's, a Canadian equivalent at McDonald's. But anyway, without any further ado, I'd like to welcome Jerry Mitrovica to give his presentation today. Thank you.
Thank you.
There you go.
Let me move away. So I stay right here, right? Yes, sir. And do I, in the usual way?
You want the Mac?
Yeah, I want the Mac. Okay, well, thank you very much. This is an honor to be the Birch Lecturer, and I thank Cindy in particular for thinking about me. I was talking a few hours ago about my first experience at an AGU. It was over 20 years ago. Dave Ewan was the convener. I don't know if Dave is here. I'm going to give an impression of him, but he introduced me. I was talking about subduction zones and dynamic topography, and I was so nervous that I broke the AGU record, which will never be broken again. My talk lasted 7.5 minutes, and I was just really happy that I didn't faint. And at the end of it, Dave, making it much better for me, looked around and said, "Okay, any questions? Nope, sit down." And then he walked up to me, and I was sitting next to Gary Jarvis, my supervisor at the time, and he said, "Hey, kid, you ever heard of the word intonation?" Now, coming from Dave Ewan, that's quite an insult, right? Okay. Well, as Cindy said, I'm at Harvard now. I used to be at the University of Toronto, and so I'd like to give this in honor of all my friends and colleagues at both of those institutions, as well as my first supervisor. I don't know if he's here, but Gary Jarvis, for starting me off and showing the way. When I accepted the job at Harvard, several people, including my niece, a little older niece, and you were talking about Cindy, said, "Well, what's it like to be at Harvard?" And I scratched my head and I thought, how should I summarize what it's like being at Harvard? And I sent her a photo over the cell phone, and this is the photo. This is a photo outside Harvard University. So I sent this to her and I said, I walk around with a dictionary, right? So this about sums Harvard up. They're wonderful people, but they need to get smaller words. Okay, so I'm going to, Rick O'Connell, I'm name dropping here. Rick O'Connell said that I needed to say something nice about Eustasy, given that I'm calling it a eulogy with this sort of cute title. And I thought it would be easy to say something nice. I could just say it's simple to understand. But in fact, in preparing this talk, I realized it's not simple to understand at all. I just pulled this off the web. Here's the title. Here's the definition. It's a worldwide uniform change in sea level caused by fluctuations in water taken up by continental and polar ice caps, or by a change in the shape of our ocean basins. So there's already an ambiguity here, and there's many ambiguities in the definition of Eustasy. In the first case, at the end, you're saying the change in the shape of ocean basins. So long-term sea level can be changed by just changing the shape of the container. So there's no addition or removal of water from the oceans in that case. But in ice age sea level, that is what Eustasy is. You take meltwater and you distribute it uniformly across the ocean. If there was no change in the amount of water in the ocean, the eustatic change would be zero. So you can see right away that we're often talking about very different things. And I'll try to show you, though, that regardless of the application, regardless of what you're looking at, this embrace of Eustasy, this idea that uniformity is so important, has really stymied a lot of progress in a number of fields. And it's, in fact, the geographic variation where all of the interesting physics lies. And that's what I've been trying to do for a long time. I'll be talking about work that stretches from the timescales of 100 million years, long-term sea level change, right into the future, the next few decades, and what we might expect from the melting of the polar ice caps. Okay, so I'm told this is very unusual. I like to stand near my thing, but I'm told that I can't do that today. I have to stand here because it's being videotaped, so it's limiting me a little bit. But this is a figure many of you will be familiar with. It's in a lot of textbooks, not this precise one, but some variation taken from a very nice paper by Ken Miller in Science a few years back, showing the so-called Exxon or Vail sea level curve. And you'll see, as well as the Vail curve, there's a revision to that curve by Bilal Haq, who I met for a second time a few hours ago. What I'm particularly interested in here are the long-term variations in sea level. This stretches all the way back 500 million years, but I'm interested in these longer order, second order or super cycles, if you will, with timescales of 100 million years or so. You can see there's a rise in sea level of a couple of 100 meters from the Mesozoic on, and then a return to lower sea level beginning in the late Cretaceous. So what is the cause of this? Well, this sort of variation in sea level is universally, and by that I mean in all the textbooks I've read, associated with the so-called eustatic change. That this sea level change, no matter where it comes from, is worldwide the same wherever you go. And part of the reason that that idea was reinforced was the mechanism that was described as a sort of causal mechanism for it. And this is a famous paper that many of you might be familiar with by Hazen Pitman in the early 70s that argued that sea level change on these long time scales was related to changes in the rate of mid-ocean ridge spreading. So in the figure on the top here, you have some stable margin, which I've sort of pulled a tree next to give you an idea of stability. You have some mid-ocean ridge in profile. What happens if you were to increase the rate of spreading on that mid-ocean ridge? What would happen is that the ridge profile would broaden, material would get farther from the ridge before it cools by a given amount, and as this broadens, it sort of lifts up the water. You're really changing the shape of the container. It's like taking a bathtub, going from underneath and pulling up the surface of the bathtub, and what would happen is that the sea level surface would go up so that the water that was at one level sometime after the mid-ocean ridge spreading rate increase would rise up to the level of the tree there. Okay, so that's the Hazen Pitman idea, and one of the main motivations for this was, or one of the reasons it's widely believed, is the argument that the high sea level in the late Cretaceous is correlated with a pulse, a period of very rapid seafloor spreading. So it seemed to work. And that correlation is important because if you believe it, if you accept this eustatic argument, it makes its way, it sends its tentacles into all sorts of fields, including, for example, geochemistry, because if you believe this, then sea level becomes a proxy for mid-ocean ridge spreading rates, which becomes a proxy for outgassing rates, etc. And this kind of correlation has been used in geochemical models. Not all models, but in some models. Okay, what's the problem with that? Well, at this vantage point, I can't actually read that, unfortunately. But the start of the problem, oh, I've got it here. The start of the problem, or the first fundamental argument against this view, really dates back to Hager in 1980. And what Brad did in an AGU, this is ringing a little bit, in an AGU talk, was, I'll read what he said that I've highlighted there. The volume of mid-ocean ridge system depends on spreading rates. But although increased spreading rates result in an increase in the volume of the ocean ridge system, eustatic sea level does not respond in a simple way. He goes on to argue that it's subduction zones. If you're increasing spreading rates, you're increasing the rate of subduction. And if you're increasing the rate of subduction, according to Brad, you introduce a kind of compensating effect for the sea level rise that would occur on the mid-ocean ridge. I don't know what that is. Somebody's sneezing back there. That might have been Brad. He might disagree with the way I've talked about his work. Anyway, I thought I was beeping, right? But okay, I'm glad that it's not me that's beeping. Now, I might quibble with Brad's mechanism for compensation. He talks about cooling rates, but nonetheless, this is really a fundamental first step. And if you're looking at modern understanding of long-term sea level change, that road begins really with that abstract. But then it goes on. 10 years later, I published a paper with Chris Beaumont and Gary Jarvis, my supervisor. It was really Chris's idea, but we tried to talk about the specific mechanism that would be responsible for this compensation. A model is there on the right. If you have subduction proceeding at some velocity, V1, I call it at the top there, what that will do, what the subducted slab will do, it will be coupled to the overlying plate through viscous stresses. And so subduction will act to tilt the overlying plate. And that tilting will produce a transgression onto the continent in this case. And if for some reason you were to end subduction, either by slab breakoff, you've accreted a terrain there, or through triple junction migration, then what would happen is those viscous stresses would dissipate, the continent would pop up. So this sort of transient tilting of continental margins, or in fact any overlying plate at a subduction zone, would act to compensate. And you don't need the end or the start of subduction to do this. If you were proceeding at V1 and then you proceeded at a higher velocity V2 sometime later, you would bring the continent down, you would cause a transgression, and that would act to compensate this effect. These ideas were also, although we argued for them in terms of a kind of a general causal effect, we applied it in that tectonics paper at the late 80s, now 20-year-old paper, to explain in particular the late Cretaceous subsidence and the tertiary uplift of the western interior of North America. This was related to subduction dynamics off that west coast. When you had active subduction, the plate tilted down, you produced the western interior seaway. When that subduction ended, the plate popped up, and now you have sediments that are increasing in depth as you move westward. Denver is a mile high for a reason, and that's the reason Denver's a mile high. But you can see, at least on a regional scale, how this would compensate for increase in sea level associated with this mid-ocean ridge. Now, a second person that was working on these ideas at the same time was Mike Gurney. He wrote a series of influential papers roughly the same time in the early 1990s, talking about all of these issues associated with subduction and ridge spreading, etc., and talking about how there's no simple correlation between ridge spreading rates and sea level. Mike's focus was, to some extent, on the transient episodes in subduction, but I think it is also fair to say that he understood, I think, more clearly the global impact of this compensating mechanism. So let me try to describe what that is. Let's revisit Hazen Pitman now, but we're going to put a subduction zone in the picture. In the top, we've got the same picture that I showed before, but on the left there, we've got a subduction zone. This is my drawing, so I apologize for the simplicity. If you were to increase the spreading rate now, you would increase the subduction rate. You would tilt that continent down, and you would lower it and produce accommodation space for the water. Because you did that, the sea level rise that you would expect on the basis of the Hazen Pitman model would not be achieved. It would not be anything like it, in fact. It would be much less. And in fact, if I take this idea a little bit further, and I argue that all subduction zones on Earth, let us say that all subduction zones were ocean-ocean subduction zones, the compensation would be complete. Any increase in spreading rate, which would tend to raise sea level, would be compensated almost perfectly by this tilting of these overlying plates, and you have no sea level change whatsoever. So this is the global implication. The reason why you shouldn't simply believe this Hazen Pitman argument that there's a simple connection, as Brad said, between ridge spreading and sea level change. But that's the first implication, but I want to talk now about more recent work. The second implication of this idea, which harks back to this idea that North America was bobbing up and down in the late Cretaceous and Tertiary, is the fundamental question was, if there is a eustatic variation in sea level, is there anywhere on Earth that you might be able to measure it? And that basic question was the focus of 3 articles published in a matter of months by 3 independent groups. The one at the top I'm involved in, so of course I'm most familiar with it, and I'll talk about it today. But many of the same arguments I'm talking about were in papers by Dietmar Müller and also Clint Conrad and their various colleagues. But the basic take-home message, I hate to use that phrase, but I just did, is the subtitle of Rob's paper here. There is no such thing as a stable continental platform. There really is nowhere that you can look and be guaranteed that you're going to see a eustatic signal, if in fact there is one. So let me go through this idea, and I'll very quickly talk about the modeling that goes behind Rob's results. This is just the last version of a series of studies by Alex Forte and I and various colleagues, Steve Grant, Nathan Simmons, Dave Rowley, and others, that deal with the idea of modeling mantle convection using as an initial starting point seismic tomography. You begin with some velocity heterogeneity. In the case of the work I'll talk about, that seismic data that was used by Nathan and Steve included 46,000 travel times. You then convert to some density contrast using a velocity to density scaling. And from there, you move, that conversion gives you buoyancy, right? Because buoyancy is the variation in density in the mantle. So that gets you one of the main inputs that you can put into a flow model. To run that flow model, to solve Navier-Stokes equation, you solve conservation of mass and momentum, you also need a viscosity profile. And for that profile, we've used a profile that Alex and I came up with a series of papers about 4 or 5 years ago now, where we jointly inverted post-glacial rebound data and mantle convection observables and found that you could satisfy both observational data sets with a 2 order of magnitude increase in viscosity. This put a lie to the old argument that glacial rebound data required an isoviscous mantle. So from that, you get these 3D mantle flow field, and with that flow field, you can then start to predict a whole host of convection observables, for example, long wavelength geoid, tectonic plate motions, dynamic topography, both at the surface and at the core mantle boundary. Now that's the usual forward approach, but what Nathan, Alex, and Steve have done is do a joint seismic geodynamic inversion. So they've taken the seismic data and the convection data, and they've inverted them together to produce a model, and that's the starting model for the simulations that I'm going to be talking about. But that's a snapshot. Now we have to go back in time, because I'm interested in how dynamic topography has varied over tens of millions of years. So we have to take that snapshot and make it into a back-projecting movie. And the way we've done that is that we simply take the conservation of energy equation, we get rid of diffusion, because of that, of course, that's irreversible. You can't diffuse back in time. You keep only advection, and you take the film. Your movie making takes this film back from the present day. Now, the way we check our results is we go back 5 million years, then go forward and make sure when we go forward using the full physics that we get back to where we started from. And then we keep doing that, and we're confident you can go back 30 million years in that approach. You can go back much longer. There are more elegant mathematical ways, particularly using adjoint methods that Hans-Peter Bunge has used, to take this 30 million years back, way back, on the order of 100 million years. And so if you want to go that far, you'd have to use a somewhat more sophisticated mathematical algorithm. But this is fine for our purpose. On the left, I think there is the dynamic topography at present day, and on the right is a global plot of dynamic topography. Oh, no, it's an ocean plot at 30 million years ago. Hard to see differences, but there are differences everywhere there. So the first thing we can do is we can say topography is just the negative of sea level. If you raise topography, you're lowering sea level. So we can take this and we can do a global integration and ask ourselves, well, forget just mid-ocean ridges and forget subduction. Let's take the whole host of vertical plate tectonics, if you will, and ask how it has changed the globally average sea level over the last 30 million years. And when you do that, you get a rather surprising result. At least it was surprising for us. You get an argument that over the last 30 million years, for this model, okay, and other models show different things, you see a sea level rise, not a fall, over the last 30 million years, a rise on the order of 100 meters. Okay? So this is the background sea level rise. The two figures, the two lines there just refer to the way we've treated the top 100 kilometers in this modeling, whether we include that buoyancy or not in the computation of dynamic topography. But this is a sea level rise. This is in the back of everything. But now let's ask the question, where are these calculations? When you look at the Vail curve, the Exxon curve, where are those curves? Where are the long-term sea level trends in those curves generated? From data from where? Typically from what people call stable continental margins, like the New Jersey coast or Northwest Africa. I'm not going to, we've computed things for both of them, but I'll focus today on New Jersey. And can we say, has that been stable enough that New Jersey in the last 30 million years would have provided you an uncorrupted view of the eustatic variation? You obviously know the answer is going to be no, otherwise we wouldn't have had that subtitle, right? Well, this is an image taken from the Simmons et al. GJI article under North America on the left, slightly different projections here. You can see at present day under North America, still evidence of the ancient Farallon plate that's now in the lower mantle. Many seismic tomographic images show that. It's now, because of the drift of the continent and also its own lateral motion, under the east coast of North America. Alex and I and colleagues wrote a paper arguing that this provided the background stress for New Madrid seismicity, for example, but that's not what I'm going to be talking about today. In addition to this cold downwelling material associated with the descent of the Farallon plate, you also have that red upwelling material, and that's not just passive flow. That's an active upwelling region that's coming up right under the east coast of the United States. So if you look at that image, it would be hard to believe when you see mantle heterogeneity like this, in this case the negative and positive 0.1% density contours, that you can call anything stable. There's clearly things happening Wherever you go, you don't just have to be on a plate margin to have vertical plate tectonics. So let's look now at a movie of what happens over the next the last 30 million years, beginning 30 million years ago as the zero. What you're seeing here on the left is a cross-section. You see the Farallon plate moving laterally and downwards, and you see this hot red upwelling pushing up under the east coast of the United States. And as it does, as those two things happen, it's tilting the east coast. That red blotch there on the right of the film shows, in fact, that the dynamic topography produced by that upwelling for this particular model is about 200 meters. So that's rather a remarkable thing for a stable platform over the timescales of tens of millions of years. So then we can write, what we've done on the right here is shown the dynamic topography after we've removed that eustatic trend for it at New Jersey. And so what's happening in New Jersey is that that region is uplifting by order of 100 meters or so, or was uplifting over the last 100 million years. But remember, dynamic topography is the opposite of sea level. If you're uplifting the crust, you're lowering sea level. So we really take the left curve, the eustatic globally average sea level, and we subtract the right curve to get total sea level. And lo and behold, you get the sea level fall at New Jersey that is seen in some of these curves. This is not a unique solution. Other models would show you different things. But it's enough to raise it as a cautionary comment that when you see curves like the Exxon curve or the Vail curve, you should not interpret them as eustatic. You should not necessarily believe that they come from a change in mid-ocean ridges. In fact, in this modeling exercise, the dominant signal is dynamic topography, and in fact, the eustatic signal is opposite from what you might expect. So that's a long-term sea level change. Now let's move to some recent work that I've been involved in looking at ice age sea level, with a particular focus on the last interglacial, 125,000 years ago. So to do this, I'm going to have to give you a 5-minute primer on post-glacial sea level change. So I hope you don't mind that, and I hope this isn't too elementary, but I want to keep everybody here, because to understand the work that we've just published on the last interglacial, you need to know some of this basic physics. So the Earth in the last million years has been characterized by a series of glacial cycles, each with a period of about 100,000 years. Each of those cycles had a relatively slow glaciation phase, followed by a much more rapid deglaciation that lasted 15,000 years. On the top left there is an image showing ice cover in the northern hemisphere at the last glacial maximum 20,000 years ago. All of that ice, on the right you see ice cover today. Okay? You had, at last glacial maximum, you had ice sheets over North America, Fennoscandia, East and West Siberia, so on. I was at a meeting in Europe a few years ago, and I made the terrible mistake of calling the Scottish ice sheet there the ice sheet at the northern tip of Britain. And 3/4 of the audience went, ugh, and walked out of my lecture. Right? So that is definitely a Scottish ice sheet. It is not a British ice sheet, right? But that happened so recently, the deglaciation extended from 20 to 10,000 years ago, that the Earth is still in a state of isostatic disequilibrium and adjustment, as manifest in all sorts of observations. At the bottom there is a slightly old eustatic curve. This is the assumption made to compute eustatic curves in ice age work. All you do is you take the ice that you have, melt it, spread it evenly. Assume there's no gravitation, Earth is rigid, spread it evenly. In this case, it's quite easy to understand, and that shows 105 meters or so eustatic trend, but it's actually closer to 130 meters, but that's the rough pattern of it. So the question is, are trends, sea level trends, eustatic, and not even close, obviously, to eustatic? And I'm going to show you some of the basic physics that gives rise to this geographic variation. This is a numerical prediction, not an observation, a numerical prediction of the way sea level is changing at present due to the ice age that ended 10,000 years ago or so. Has nothing to do with modern melting of ice sheets. It's all just a remnant ice age effect. So the important thing to realize is this is at present day, in this model, there was no change in ice over the last 3,000 or 4,000 years. So any color other than 0 here is non-eustatic. Okay, because a eustatic assumption would be 0 here. Sea level isn't changing, but of course it is. In the near field, but near field I mean close to the location of the ice sheets, where you have the deep reds and blues in the north and south, and in the far field, these sort of orange and yellow colors, at least from here. Okay, so let's look at that physics. This figure is actually taken from a paper by Glenn Milne and I, in which we were focused on the far field. So the color scale there is saturated in the near field. In the near field, like over Canada, where you have that deep red, sea level is falling by 1 centimeter per year or so. So that's well to the left of this plot. You'd be down the hall and outside the building, because this plot goes up only to roughly about 1 millimeter per year. And the reason for that, the cause of that is well known. Of course, this is just post-glacial rebound. You covered this area with ice, you took the ice away, the crust rebounded, and it's still rebounding by 1 centimeter per year. Surrounding those areas of rebound, you have the peripheral bulge, these blue regions. On the right, you can see when you placed an ice sheet down there, you produced the bulge. When you took the ice sheets away, this central region uplifted, but those peripherals, forget it, subsided. And when they did, sea level rose 2 to 5 millimeters and continues to rise by 2 millimeters per year or so, for example, off the East Coast and along the East Coast of the United States. Of course, it's hard to see those areas because they're getting progressively submerged. Geological markers for those are underwater, but markers for sea level or post-glacial rebound are everywhere. You just have to fly over Hudson Bay and you'll see a picture like this. This is a classic picture of parallel beaches. One beach was formed, the region uplifted, the next beach was formed, and so on. So you get this classic picture of parallel strand lines, what the old-time geologists would call emergence of the land and what we now call sea level fall. So that's sort of straightforward to understand, the near field. The far field, in particular this sort of orange and yellow area of sub-millimeter per year sea level fall, ongoing sea level fall, happening today because of the ice age, is a little bit harder to understand. This is a mechanism we call ocean siphoning. It's shown on the top right there. What's happening is you have all these peripheral bulge regions over the ocean. As those peripheral bulges subside, water has to migrate into them in order to maintain hydrostatic equilibrium. You're basically taking an object out of the ocean. It's like having a swimming pool with an object submerged at one end, like a hockey puck, being Canadian. And you take that hockey puck away, what's going to happen? The surface of the pool is just going to drop. And it'll drop even at the far end of that swimming pool. In the same way, you're taking that hockey puck out, you're relaxing these peripheral bulges. Water is moving into them from the far field, and it's causing far field sea level to change 0.5 millimeter per year. That doesn't sound like much, but 0.5 millimeter in 4,000 or 5,000 years adds up to 3 or 4 meters. And so if you go to the equatorial Pacific, this is an exposed coral on an equatorial Pacific island. This is a feature that's endemic to those regions. These are called 3-meter corals, 3-meter beaches, etc. You wouldn't be blamed if you were sunning yourself close to this to think that this must be due to some local tectonic effect. But in fact, that coral is exposed because of the ice age. It's exposed because water is moving out of those areas, moving towards the peripheries, causing sea level to drop about 0.5 millimeter per year, which adds up to about 3 meters. But think about what this means for Eustasy. If you were to believe in Eustasy, you would look at this curve and you would conclude that ice sheets have grown sufficiently to lower sea level by 3 meters, and you'd be completely wrong. Ice sheets haven't done much at all in the last 5,000 years, but sea level has kept changing. And it's this dynamic effect on sea level that is so important, because what I'm now going to go to is an application that tries to look at local sea level and tries to convert that by correcting for these kinds of physics into global sea level, into a true eustatic measure or an ice volume measure. And I'm going to be looking at the last interglacial here. Why is it important? We know, as I've said, that the Earth has gone through these ice age cycles. The last time we were in interglacial like we are at present day, we call that isotope stage 5e. I have no idea where these terms came from, and in fact, I just learned some of them to get ready for the talk. If you're in Northern Europe, you'd call it the Eemian stage. That I did know, actually. That occurred around 125,000 years ago. You see my 5e label. Why is that such an important place to understand? And it's important for a variety of very straightforward reasons. At the last interglacial, at the Eemian, 5e, polar temperatures were known to be about 3 degrees higher, 3 to 5 degrees higher than present. In fact, there are some temperature profiles shown there in the bottom left, published in a News and Views article by Peter Clark and Peter Hybers. So 3 to 5% in the poles, 1 to 2 degrees of global warming, because the poles will always warm more than the global average. And you can see that in the profiles down there. So think about that. At current greenhouse gas concentrations, even if we do nothing else, temperatures will rise on the order of 1 to 2 degrees, globally average, right? So that's why the EMEAN 5e is considered to be such an important analog for what we're about to do to our climate. What happened at 5e? What were the ice sheets like at 5e? What were their extents? These are fundamental questions that we need to ask, and the answer will provide us with one very good data point as we move into a globally warming world. This is a picture I saw Bill earlier. Bill sent me this from Woods Hole of a last interglacial sea level marker, Porites and Acropora palmata. I hope I've said that right, Bill. This is not so far from where I was born, but I didn't know that at the time. So this is very typical. In fact, Western Australia produces a number of the very important points in last interglacial sea level studies. But regardless, if you go around the world and you look for these markers that show sea level at the last interglacial, you take the rough average of these local markers, they indicate that sea level at that time was 4 to 6 meters above present sea level. That's the typical quote. And that is used to argue that as we move into the warming world, we have 4, 5 meters still left to go of melting of the polar ice sheets until we get back to the level at the same amount of warming that we were at the last interglacial. But as you've seen with my little primer on Ice Age sea level, you don't want to do that. You want to correct these for those dynamic effects. And this talk couldn't be timed better because this paper in Nature just came out. In fact, it's published tomorrow. It's a paper by colleagues at Princeton, Bob Kopp, Frederick Simons, Adam Maloof, and Michael Oppenheimer, that does just this. I've highlighted it in the red. I won't read it to you. What we've done in this paper is we've taken all of the data points that we had at our disposal, all of the last interglacial, put it through a statistical analysis that included the basic physics of glacial isostatic adjustment, that these things were happening to change sea level regardless of what ice volume was doing. And out the other side came an estimate of the true ice volume or eustatic change from LIG to present. And I hope I've given you enough motivation to understand why that is such an important question. So these figures are all taken now from Bob's paper. This is a figure showing a site location map. The colors there represent how many data you have. I can barely read it. Blue is 1, green is 2, and so on. So they're widely distributed. And this is important because before I started this work with Bob, he asked me to join in the study. I said, Bob, these are all far-field sites, everything around the equatorial Pacific. I can already tell you how your estimates of sea level are going to be biased because they're roughly all in the same area, but I was wrong. That the distribution of these is everywhere, near field, far field. They're sampling the dynamics all over the place. And so the correction isn't easy to understand. You can't know which way the number is going to go until you do the study. So Bob is going to cringe here. The paper in Nature, the statistical analysis is given on the bottom right, but I've translated it, if you will, into this sort of main figure, and I hope he doesn't feel insulted by that. But basically, being a Bayesian at heart, it's a Bayesian framework. We start with this sea level database. That database is noisy. It's noisy because we don't know the ages that accurately, although Bill tells me that we'll know them more and more accurately in the next few years. And they're sparse. They're not always where we want them. They're all over the place. So we have that, and that provides us with what you might call an empirical data covariance. We then include Ice Age models. So my work was to provide Bob with the results of thousands of Ice Age runs, right? That varied all sorts of parameters in the Ice Age calculations, including the eustatic difference in sea level, where the ice was coming from, etc. And that gave us a covariance between local sea level, global sea level. We stick this in a Bayesian framework, and out comes, with a lot of work, the posterior probability density function. So again, my apologies to Bob. So that's what's shown here. I'm going to actually just summarize these in the next plot, but I want to give you an idea of what these look like. At the left, that's a probability, a posterior probability, as you move through the interglacial, 120 to 125,000 years, of global sea level. So I'm using global sea level now as synonymous with eustatic sea level, spread evenly, okay? And you see that it varies, and you have sort of plus or minus 2 sigma envelopes. It's varying along there. The same on the right, that's not global sea level, but the rate of global sea level. I don't want you to understand the details of this. Suffice to say, if you have these probability functions, and of course there are also correlations that can't be shown on this plot, you can start doing some hypothesis testing, and that's what we did. And these are what Bob calls exceedance probabilities. And if this talk's going to go wrong somewhere, it's going to be in the description of these probabilities. But what these are maps. So for example, let's take the solid black line there. Do I have a pointer? Yeah, the solid black line here, okay? That shows the probability that global sea level sometime in the last interglacial exceeded a certain value. So the 95% probability, shaking here is completely magnified because I'm so far, 95% likely that sea level in the last interglacial was global sea level, eustatic sea level, was 6.5 meters higher than it is today. So right away you see 4 to 6 was a significant underestimate. It's at least 6.6. We're extremely confident of that. Then you move along this curve, the 66.7% confidence is at 8 meters. We're 67% confident that last interglacial sea level exceeded 8 meters. If you work in the last interglacial sea level game, and there's a few people I can see you out there, this is a stunning result, right? Most people thought 4 to 6 was maybe, if anything, a mild overestimate, but in fact it's a significant underestimate. Right? Sea level was at least, I think, 8 meters higher at the last interglacial than it is today. The second curve here, this dotted line, that's the probability, the exceedance probability, that each of the Antarctic and Greenland ice sheets both lost at least this much at last interglacial relative today. So, for example, we're 95% confident that the Antarctic and Greenland sometime during the last interglacial lost at least each 2.5 meters of equivalent eustatic sea level. Not necessarily at the same time. We can't say that that loss happened at the same time. But at some time in the interglacial, that was true. So what was that world like? Here's several images that give you an indication of, of what this all means. The top there is a plot taken from a science study by Otto Bleisner et al. From a few years back. They argued by looking at last interglacial climate that the worst that could happen is that the Greenland ice sheet and circumarctic ice fields would lose enough to raise global sea level about 3.5 meters. That's a worst-case scenario. At the bottom there's a recent paper by Jonathan Bamber et al. That talked about what would happen if the West Antarctic ice sheet collapsed. And Bamber made the argument that you would lose all marine-based settings, all marine-based ice sheets, and you would raise global sea level, in that case, by about 3.2 meters. There may also be a difference in thermal expansion between last interglacial and today, because it was a bit warmer, but we're heading to that world after all. So this tells you, if you add up all of these scenarios, you get about 7 to 7.5 meters. So what this study tells you is rather shocking, I think, in a sense. It tells you that at last interglacial, we are pretty darn confident that this is what the polar ice sheets look like at some point during that interglacial. We're looking in these figures and seeing the last interglacial world. And this is where we're headed if that warming raises globally average temperatures a degree or two. We're headed towards polar ice sheets, and at least in the marine-based sectors that have completely collapsed. And as Bob says here, the last line in Bob's usual understatement, the results highlight the long-term vulnerability of ice sheets to even relatively low levels of sustained global warming. And that's the proper sentence. Those who know me know that I probably would have written something a little bit more dramatic than that, but Bob is more conservative, and justifiably so. This is an important issue. Right? So now let's move to the last section of the talk. This is this idea that's emerged in the literature recently very counterintuitive idea of 20th century global sea level change. What did sea level do in the last 100 years or in the last few decades? How will we know what sea level do? Well, anybody who's mainstream in this field, anybody who's looked at tide gauge data or even satellite altimetry data, would argue that sea level rose in a globally average sense by about 2 millimeters per year over the 20th century. Okay? That's fine. The question is, there's a lot of geographic variability to that. If you go to this tide gauge or to that tide gauge or to another one, it can vary by orders of magnitude. In fact, it's very common to see tide gauges that show a sea level fall, not a sea level rise. And if you go back, you turn back the clock maybe 6 or 7, a little bit longer than that years, if you were a person who'd like to believe that climate change was not happening, this was one of the main arguments against it. Because the belief was, if you're melting polar ice sheets, water should be going up like in a bathtub. There's no reason for this geographic variability. But as I'll show you, that geographic variability is a necessity. So I'll take you through a tide gauge analysis. It's a few years old now. This is an analysis by Mark Tamasey, Jim Davis, Glenn Milne, and I, published in Nature a few years ago. We could do all of this for satellite altimetry data, but I think it's nicely shown in this tide gauge data. A reviewer of that article said that they wouldn't believe it unless we showed the effects that we were talking about for a specific set of tide gauges, sites, and that was a set that was promoted by Bruce Douglas. I guess it's 1997. About 24 sites that Bruce said were the perfect sites to look at 20th century sea level rise. It was away from places that might have groundwater pumping contamination, away from convergent margins, and that had enough data that you could separate a long-term trend from a decadal fluctuation. I see movement, and I guess I'm nearing my end. Okay, and the site there is at the bottom left there. I just pulled that off the web. That's a tide gauge site in England, not Scotland, in England. And I joked to somebody earlier that the second arrow pointing to that small hut, we have no idea what that is. We just think it's a toilet. So what do you get when you go to those 24 sites and you look at long-term trends, 20th century trends? Well, these are European sites. These are sites, you can sort of read them, I hope, New Zealand, Honolulu, Western United States, South America, East Coast of the United States. And this is in millimeters per year. So this is a long-term trend you'd get in the tide gauges. And you see that it's varying all over the place. You also see some very classic results. The European gauges all show rates that are lower than the global average. And that has a name in some papers. It's called the European problem, right? And that's not a geopolitical comment, right? That there is sea level tends to be smaller in Europe than elsewhere. And then you take the average. In this case, the average was about 1.6 millimeters per year, and you hope the variability goes away. But taking that average implies that you believe the bathtub. You believe that if you rapidly melt an ice sheet, sea level rise is uniform. This is the bathtub model. This is Eustasy, okay, called the bathtub model in modern climate studies. But in fact, that is completely and utterly wrong, right? It turns out that the physics is better shown on the right. An ice sheet exerts a gravitational attraction on the water around it. If you melt that ice sheet, two things happen. You certainly add water into the oceans, that's for sure. You're increasing the globally average sea level. But you also relax this gravitational attraction. Water will move away from the ice sheet. And believe it or not, close to the ice sheet, sea level falls. If you're standing at, well, let me wait before I say that to show you one of these fingerprints in action before I tell you where you should panic and where you should not panic, right? Now, of course, this is highly exaggerated. We don't have a water-free ocean. But nevertheless, you can see this hinge point. So how close is close? It turns out close is not close at all. It's 2,000 kilometers. So within 2,000 kilometers of a melting ice sheet, sea level will fall. So let me give you an example of a numerical test where we've taken off enough water from Greenland that eustatic sea level, the globally average sea level, would rise a meter. What actually happens? If it was uniform, then you would just see one number here, 1. But in fact, around Greenland, you have this deep blue. That's an area where it's actually falling. So that's what I was about to say. If you happen to live, yet again, in Scotland, you have a friend, and that you know that the Greenland ice sheet is going to catastrophically collapse tomorrow, You might call him being justifiably concerned, but there's no reason for concern, except in a general human sense. Sea level will actually fall in Scotland, it'll fall in Newfoundland, and it'll rise progressively more as you move away from that ice sheet. That is a fingerprint of melting from Greenland. And you can get similar fingerprints from the Antarctic at the top and from glacier melting. So the question is whether the variability we see, that variability shouldn't worry us. That variability is absolutely necessary if these polar ice sheets and ice reservoirs are contributing to the global sea level rise. It is through this variability you're really adding one fingerprint and another fingerprint. And to show you how that works, this is a non-unique solution because we don't yet have an accurate, or at the time we published this, we didn't yet have an accurate fingerprint for the thermal expansion effect on sea level. But this shows you a fit you can get to that same data if you add, in a least square sense, a best weighting of those three fingerprints that I talk about. And you can see that the fit is very much improved. You solve the European problem. Not surprisingly, in this case, you're solving the European problem by melting from Greenland. And one of the main conclusions of this study is that Greenland melted in a globally average sense by about 0.4 millimeters per year over the last few decades. Enough, the sea level impact of that would be felt less in Europe than elsewhere because of this fingerprint. I want to just alert you now to the fact that these kinds of studies have matured quite significantly since we wrote that original paper. There is a poster that I'm involved in by Neil White and colleagues, there's a bunch of us on it, on Friday, that talks about using these fingerprints now in combination with steric fingerprints, using not just tide gauge data, but satellite data, satellite-based altimetry data, to understand, to get constraints on this geographic variation and to more accurately fingerprint. The result I showed you was simply a test to show you that you should embrace that variability because it tells you something from a climatological sense more important than just the mean sea level rise. It actually tells you where the water's coming from. And that sort of application has been used. I have just 3 more slides, if that's okay. Probably 6, but I said 3 when I saw them, right? One of the most, I think, one of the nicest applications of this work was by Peter Clark. I was on this paper with a number of colleagues, Mark Tamasy, Glenn Milne, etc. One of the most rapid sea level events in the Ice Age was Meltwater Pulse 1A. This was an event 14,000 years ago in which sea level rose 20 meters or so in less than 200 years. Remarkably, we don't know where that water came from. The typical argument is that water came from North America, the Laurentian ice sheet. And the primary argument for that is that that ice sheet was just really big. And so if you're going to get that much water, it better come from a bigger ice sheet. Well, in this paper, what we showed was there are actually 2 curves, and there's about to be 3 that just reinforce this conclusion. But 2 places on Earth, Barbados and Sunda Shelf near Vietnam, where we actually have a record of sea level rise across this meltwater pulse. And when we look at those curves, we see that sea level rose by the same amount here as here. If it had come from North America, the sea level rise in Vietnam would have been 50% bigger than the sea level rise in Barbados because it's so much further away from Laurentia. If it came from the Antarctic, the sea level rise would be the same. This led us to a conclusion in this paper that it was the Antarctic collapse that caused the Meltwater Pulse 1A. This has engendered a lot of debate, to put it mildly. Many people simply don't believe this argument, but sea level is pointing here. There's a new curve coming out for Tahiti which reinforces this argument. So I'm still a firm believer that Meltwater Pulse was sourced to the collapse of the West Antarctic ice sheet, which is even more concerning as we move forward into this world of ours. And let me just finish with one other, this isn't a full study, it's just a paper that I published recently, in particular with the graduate student Natalia Gomez. I hope Natalia is here. Peter Clark, again, looking at what would happen if that West Antarctic that everybody's worried about melted catastrophically. And there's a reason we're worried about the West Antarctic. It's mostly a marine-based ice sheet, and that makes it susceptible to collapse. It has ice shelves that are buttressing it, keeping it together. If those ice shelves collapse, it all just spills out. What happens if that happens? And we thought it would be nice to show people what the sea level rise would be if the West Antarctic ice sheet melted. So we basically just took it all off. There's another paper that was published soon after that said if the West Antarctic ice sheet melted, it wouldn't all melt. Mainly only marine-based sectors would melt, but that wouldn't change the geometry I'm about to show you. Old fingerprint, believe it or not, refers to the fingerprints I've been describing to you. This gravitational effect plus the fact that the Earth deforms. Not only is water move away from the melting ice sheet, but because the ice sheet melts, the land uplifts. All of that was included in those fingerprints I showed you when we looked at 20th century melt. But in the case of West Antarctic, we're hurt in two other ways in North America. It turns out that when you do a calculation where the whole ice sheet goes, rather than a thin sheet, as we would expect in the 20th century, sea level rise is accentuated, in particular in North America. And you're supposed to see this. This is all normalized by the eustatic variation. So whereas a classic paper from the 70s argued that the sea level rise you'd see in North America is 10% higher than the average, we showed in this paper, science paper, that it would be actually closer to 30% greater than the eustatic in North America. Why is that? Well, strangely enough, the physics kills you here in two separate ways. One is, this is another one of my cartoons, you can see them already. If you melt the West Antarctic ice sheets with sitting in the bowl, people like to think, well, we're okay. What's going to help us is that it's sitting in a bowl. So when the ice sheet melts, that bowl is going to hold a lot of water. And so previous calculations just assumed the hole would carry a lot of water, but the problem is the hole rebounds. And as it does, it throws water out into the global ocean, and it accentuates sea level everywhere. But in North America, we get a double whammy, right? And the second thing is rotation. It turns out if you melt the West Antarctic ice sheet, all of it, you will drive the rotation pole towards the West Antarctic by about 1/2 kilometer. And that will move, sea level is on this oblate spheroid as we talk about it. It will cause that spheroid to reorient, and that reorientation will cause a rise in North America and the South Indian Ocean and a fall in antipolar quadrants. So you get hit here and here. North America gets this double whammy. If the whole ice sheet melts, if the whole entire West Antarctic ice sheet melts, the eustatic estimate would be that sea level will rise 5 meters. Unfortunately, the peak sea level rise just happens to be off the coast of Washington, D.C., and that sea level rise would be 7 meters, right? So we were quite worried when we saw that because we thought, well, who knows what people are going to think. But that is where it is. It's about 40% higher than the rise. It's also that high on the U.S. West Coast, and it's almost that high in the Southern Indian Ocean. So here are my conclusions. The first is that there is no simple understanding of Eustasy. It means different things to different communities. As I've told you, Ice Age community doesn't even think of Eustasy unless an ice sheet melts or grows. Long-term sea level variations, as Brad said in 1980, aren't simply linked to mid-ocean ridge spreading, right? In fact, they are linked to the whole plethora, I'm looking for a synonym for, plethora of 3D or vertical plate tectonic effects. That subduction zones and mid-ocean ridges everywhere in the ocean contributed to it. And you cannot, there is no magic dipstick, as they call it. There's no remarkable ruler sitting out there somewhere on a stable platform that is going to tell you what Eustasy is. All of those platforms are moving up and down by tens of meters, hundreds of meters, so you're out of luck. But that's okay. Don't throw up your arms. That geographic variability tells you something. It tells you something about the dynamic variability in this convective system of ours. It tells you something important. Last Interglacial Sea Level, the paper that's coming out tomorrow in Nature, the article. It tells us with this statistical approach, combined with a sea level physics, not simply a eustatic approximation, that Greenland and the West Antarctic ice sheets were largely gone at the last interglacial. And as I say, that's a very disconcerting conclusion, because there's almost no doubt we're heading towards a globally average 1 to 2 degree warmer climate, even if we stop doing what we're doing. And so we're heading towards that last interglacial condition. And finally, recent and future loss from the polar ice sheets will be accompanied by this variability that's incredible. A variability that tells you with a few very accurate measures of sea level. You're sitting there in the middle of the ocean and you have some 3 or 4 very accurate sea level measurements. You can say something astounding. You can not just take the average, you can do a least squares analysis and pinpoint where that water's coming from. It all looks like water to you, but that variability tells you something. But that variability is also a concern for North America if the West Antarctic ice sheet, as we fear, ever collapses. So thank you very much.
I know some of you have to go out quickly to change your timeshares for the East Coast of Maryland and North Carolina, but no, just joking. Sorry, bad joke. And I'd like to take a couple of, also for any of you who have been disadvantaged and missed the talk because it was doubly listed at 4 and 5 o'clock, our apologies, we've made the most we can. Could we maybe take a couple of questions and then appropriately acknowledge Kai Johnson's award? Are there any questions? Harry.
Why were you crazy enough to move to Harvard?
No, don't answer.
I love it there. I walk around with my dictionary.
Deep water.
No.
Right. Coastal. Well, I was born in Australia, so I'm going to live and I'm going to die near the ocean. That's the...
Do I see any other hands? Yes.
How long will it take to get the 8 meters from Washington, D.C.?
Well, it's actually a little bit less than 8 meters, but of course, the comment people should be aware of is that we may be having already started that process, but ice is, well, you certainly know this from Toronto, where the big mounds of ice last well into April and May sometimes. Because of the albedo of ice, it's hard to melt it away. Most people think 200 to 300 years once the climatic warming starts, at least. So the process will begin, has begun, who knows, but the process will take several centuries to collapse an ice sheet the size of the West Antarctic, or more. Some would say more, of course. I'm going to be attacked by the polar ice sheet community.
If you had two choices now, you had a certain amount of money, would you spend it trying to stop what you're doing in terms of burning a resource that's going to run out anyway, or preparing for this onslaught of the rising sea level underground?
Yeah, I think that's a very involved question. I don't happen to, I'm going to answer, as I once joked with the NSF panel, I'm going to be a politician and answer the question I want to answer, not the question you asked me, right? But I don't think it's a zero-sum game. I think that's the issue. I simply think you have to do both. I know that sounds like an escape. I could be glib and say that extra money can start helping to pay for my summer salary. There is no such thing in Canada, but I've found out that they exist in the United States. But I don't think it's a zero-sum game. I think you have to do both. These processes are going to take hundreds of years. I think it's just, if anything, this should just be a catalyst to change. I really know that it sounds like I'm punting that question, but I don't really know any other way to answer it. Yeah, no, well, that's from last interglacial to today, but you're quite right. As we move into a warming world, most sea level people who look at data argue that in the 20th century, ice melt dominated. Thermal expansion, well, most, not all, was a minor player. But as we move forward into the next century, most people, most talks I've seen by people who are the experts in this field suggest that thermal expansion is going to catch up and overtake it. So in the 21st century, the bulk of the sea level rise we may see will be through thermal expansion. And what that means is to complete this fingerprinting exercise, one needs a very accurate estimate of the thermal expansion effect. And that's hard to do for two reasons. You need these measurements close to the coastlines because that's where you're taking them, but you also need deep ocean because the deep ocean contributes to the package of thermal expansion as much as the shallow top 500 meters. So that's a very, very difficult technical problem to solve, but it's being solved, and eventually we'll have a fourth fingerprint up there for thermal expansion, but I don't think we do now.
Okay, there was one more question. Yeah.
Sorry? So in a sense, you're mixing two timescales, but that, of course, increased spreading rates will have some geochemical effect on the system. But the thermal expansions that we're talking about are over century timescales, and there'd be no effect whatsoever with those.
Great. Well, thank everyone so much. And what I'd like to now do is recognize Kai Johnson. And I don't think I can get the power, well, I could, but I'd just like to recognize him as the first of the Tectonophysics Early Career Award winners. Kai, for his breadth and depth of knowledge and his extreme generosity in sharing that with his colleagues and students. So thank you, Kai.
Thank you.